Recording's rolling. It's Thursday, November 6th. So here's top mathematician for Module 4. So awesome job if you made top mathematicians list on Module 4. So this quiz is I do have returned to you guys. Those are in your return folders. So if you want to complete corrections, you can do that. Give you partial credit back. Yeah. And then, main thing we're doing today, lesson 5.3, proving polynomial identities. Actually, this lesson, I don't think there's very much super unique. We're still on polynomials. Actually, I think it looks kind of a lot like last lesson. Had all those identities, right? But here, we're just going to prove that. So here, of course, I followed a bunch of these ahead of time. Try this a little different here is I'll just point out to my notes, use my notes, how some of these might work. So, for example, if they gave you this identity, like a to the power of 5 minus b to the power of 5. Now, supposedly, that should be equal to this expression, a minus b, a to the 4, a 3b, a squared b squared, a b3, b to the 4th. Yeah, supposedly, which I wrote right here. Now, what you can do is you can have an equal sign, but then put a question mark above that because maybe you don't know, right? And I'll show you at least one example where it did not work out. Right? So, is this really true? So you can either leave one side the same and then manipulate the other side, right? Or you can manipulate both sides. They did that for some examples in the lesson also, right? Until both sides match. And if they both match, then the left side is in fact equal to the right side. And if they don't, then it didn't work and the identity is disproven. So in this case, I did the super distribution. I multiplied this A by all 5 terms in here, got 1, 2, 3, 4, 5 terms, and then multiplied this negative B by 1, 2, 3, 4, 5 terms, got another 5 terms. So I have 10 terms over here. Now, it turns out that a bunch of these canceled out. These two cancel. So what you're left with is a to the 5 minus b to the 5, which is exactly what the left side looks like. So then you effectively prove this identity. So that's all. And really, all items are like that. There's some fun word puzzles. Like we got this triangle set up, and it says with plastic claims that some expression is true. Like if you have this leg triangle, this leg of the triangle, then I can say the hypotenuse is always equal to this, right? How can you show that? Now, if you're allowed to know Pythagorean theorem and take that to be true, then you can test that with Pythagorean theorem. And I also solved that one out. That goes right in front of me, but it's on the main video that I'll also roll for you guys. Or actually, these next two examples are also geometry examples like that. It's like, what if you have a square that's 3x plus y on one side and also 3x plus y on the other side? Can the total area of the square be defined by this expression? Here, it's right here. Okay, so okay, so the area of a square is the base of its height, which I expanded out here, and then you can FOIL this. Right? And on the right side, they said, well, supposedly it's equal to this expression. And in fact, that did turn out to be true because the left side matches the right side. So that works. There's a little bit more complicated example with this rectangle, this blue rectangle. They define in terms of x and y. Okay. So I solved this out, and that also worked out to work out that way. Let's see, one that did not work out. If I skip down to, I think number 13, yeah. So this whole section here, the premise is determine whether each equation is an identity. So maybe some of these work and some of these don't. And now number 12, I did get to work out, so that one works, right? But number 13, I'll show you guys right here. I said, does the left side match the right side? And there's a couple ways you can handle this. You could distribute everything on the left and then distribute everything on the right. So you have a giant polynomial on the left and a giant polynomial on the right. I went the exact opposite way. I said, well, I could just take the right side and I could factor this bit, which I did right here. And then I compared left and right. It's like, well, this x minus 1 matches, but nothing else does. This is different. This is different. I mean, it's kind of close, but if you look really close, it's actually a little bit different. So this is actually not an identity. So that one failed. And one more I want to point out to you guys that was kind of interesting was because just a different way to think about it is what if you have a table of values? So they have this expression here on the left side equals this expression here on the right side. Now, you could solve this in terms of variables, like every single other example that I showed you guys today, just in terms of x. But I remember that these variables could represent numbers. Like you could plug in numbers for x. So if I call this f of x and I call this g of x, right? And what if you make a table? Now they did recommend some x values. They said 0, 1, 2, 3, 4, right? Which I just copied here. And then I made up one of my own. I said, what if I plug in pi? And I plugged that into this expression on the left, this expression on the right, and I got the exact same sets of numbers all the way down, even for this crazy number that I just picked. That exactly. So you could pretty reliably say that these two expressions would be the same. Okay. And then I'm sure if you show that to the variables, you would get the same result. All right, so there you go. That is a rundown of 5.3. Again, I don't think there's anything super new there that you guys haven't seen before or couldn't do, but give you guys some examples of what that looks like. So give you guys time, of course, to work on your Alex today. And if you have questions, call me over. I can help you out. Or if you want to do quiz corrections on Module 4, or you got questions about those, you can work on that too.